Hey there, and welcome to The Explainer. Today, we are diving deep into something we see every single day, the science of light. We're to look at how it travels, how it bounces around, and, how it makes that reflection in the mirror even possible.
I mean, it seems almost boringly simple, doesn't it? You look in the mirror and yep, there you are. But what is actually going on there? Behind that simple reflection, there's this incredible dance of physics happening. And trust me, by the end of this, you are going to see it in a whole new light. So let's jump right in.
Okay, so before we can even think about that mirror, we've got to get to know our main character in this story, light itself. What even is it, and how does it get from point A to point B?
So at its core, light is just a form of energy. It's what's called an electromagnetic wave, and it zips around in these perfectly straight lines we call rays. I mean, this is the very reason we can see anything at all, from the screen you're looking at right now to stars that are light years away.
And get this, light is insanely fast. In a vacuum, we're talking 300 million meters per second. That is the universe's ultimate speed limit. Nothing goes faster. To put that into perspective for you, a single beam of light could whip around the entire Earth more than 7 times in the blink of an eye. Just 1 second. Wow.
Yeah, and light plays by its own set of very cool rules. So you know how sound needs something to travel through, like air or water? Light doesn't. It can just cruise through the total emptiness of space, no problem. And here's a real mind-bender. It has this dual nature. Sometimes it acts like a wave, and other times it acts like a little particle. It's both.
All right, so we know what light is and how it zips around. But where does it even come from? Where is it born?
Well, you can basically split the entire universe into 2 teams, the light makers and the light bouncers. On one side, you have your luminous objects, things like the sun, stars, even a plain old light bulb. These are the sources. They're making their own light. But then you've got everything else, the non-luminous stuff. We're talking about your book, your chair, heck, even the moon. They don't make any light at all. The only reason we see them is because they're reflecting light from one of those luminous sources.
And speaking of making lights, some creatures have this down to a science, literally. It's called bioluminescence. Think fireflies. It all starts with a molecule called luciferin. That's the fuel. Then an enzyme called luciferase acts like a spark plug, setting off a reaction with oxygen. And the result? It produces what's called cold light, which is amazing because it gives off almost no heat. It is, for sure, nature's most efficient light bulb.
Okay, so our little ray of light is born, it's traveling at this mind-boggling speed. But what happens when it actually hits something? Well, that's when its journey gets really interesting.
You see, when light hits an object, a few different things can go down. If the material is transparent, like a window, light just sails right through, and you get a really faint shadow. If it's translucent, like frosted glass, the light gets all jumbled up and scattered as it passes through, which gives you a much softer shadow. And then you have opaque objects, like a brick wall, which just stop the light dead in its tracks. No light gets through, and that's how you get a nice, dark shadow.
And this simple idea of blocking light has been used to create absolutely stunning art. For centuries, traditional shadow puppetry in India has used these opaque puppets and a light source to bring epic stories to life. It's just a beautiful, creative use of some really basic physics.
Okay, here we go. We've reached the main event. We get shadows now. That's cool. But what about reflections? What are the actual rules that make light bounce off a surface in just the right way to create that perfect image of you in the mirror?
So to really get reflection, we just need to know 3 key players. First, you've got the incident ray. That's just the light coming in. Then you have the reflected ray. That's the light bouncing off. And finally, there's something called the normal. Now, this is just an imaginary line we draw that's perfectly perpendicular, at a 90-degree angle to the surface, right where the light ray hits.
Okay, so the first law of reflection is super straightforward. It just says that all 3 of those things we just mentioned, the incoming ray, the outgoing ray, and that imaginary normal line, they all exist on the same flat surface. Like, you could draw all 3 of them perfectly on a single sheet of paper.
And now for the second law. And this one is so elegant, so powerful, it's simply this. The angle of incidence is always equal to the angle of reflection. In other words, whatever angle the light comes in at, it bounces off at the exact same angle. This simple, beautiful rule is the secret sauce behind every single mirror.
So, have you ever wondered why you can see yourself perfectly in a mirror, but not in, say, a white wall? Well, it all comes down to this second law. A mirror is incredibly smooth, so all the parallel rays of light coming from you hit it and bounce off in the same direction, perfectly preserving the image. We call that regular reflection. But a wall, even if it looks smooth to us, on a microscopic level, it's super bumpy and rough. So when light rays hit it, they all hit at different little angles and scatter in a million different directions. That's irregular reflection, and it's why you don't see your face staring back at you from the drywall.
So now that we know the rules of the game, let's check out some of the seriously clever ways we humans have put them to work.
A periscope is just a perfect example of this in action. It's so simple. It just uses two mirrors, each one tilted at a perfect 45-degree angle. Light comes in the top, bounces off that first mirror, zips down the tube, hits the second mirror, and bounces right into your eye. It lets you see around corners. It's simple, but totally brilliant.
And then there's the kaleidoscope, right? It uses the exact same principle, but instead of for spying, it's for creating art. You've got these three mirrors inside, all angled toward each other. And those little bits of colored glass at the end, they get reflected again and again and again, creating these stunning, symmetrical patterns that are always changing. It's basically a playground for the laws of reflection.
So the next time you look in a mirror, you'll know. It's not some kind of magic, it's just the elegant, predictable science of reflection at work. We've figured out how light travels and how it bounces. But what happens when light bends? Well, that phenomenon is called refraction. And that, my friends, is a story for another explainer.